We're going to be practicing using the Pythagorean theorem. We'll do some examples and then we'll talk about some applications and solve some word problems. In order to use the Pythagorean theorem, first we need to be able to describe parts of a right triangle. The Pythagorean theorem uses those parts in its formula. So first off, across from the right angle or opposite from the right angle is always the hypotenuse. And the hypotenuse is always the longest side in a right triangle. The other two sides are called the legs. One of the legs could be called side A. Side A is always going to be across from angle A. Another side could be called side B, and that would always be across from angle B. If your triangle is not labeled with A, B, and C, well then it really doesn't matter which leg is which, as long as you don't label them as the hypotenuse. So always when you see a right triangle, look for that right angle, look across from it or opposite from it, and label that side the hypotenuse, and then it really doesn't matter which side your legs are. Typically, Pythagorean theorem is described as a squared plus b squared equals c squared, where c is represented by the hypotenuse. So your hypotenuse length will always be by itself, being squared on one side of the equal sign, while the legs are going to be squared and added on the other side of the equal sign. So common mistakes are to mix those up. Always put your legs on one side and your hypotenuse all by itself on the other. If you don't like to describe the Pythagorean theorem using A, B, and C, well then use words instead. Legs squared plus leg squared equals the hypotenuse squared. To solve for the hypotenuse, if you wanted to get fancy, well, we would square root both sides. So the hypotenuse is equal to the square root of the sum of the squares of each leg. So when we find the hypotenuse, we're going to add the squares of the legs. Make sure that you use your exponents before you add. Another common mistake that tends to happen. In letter form, here it is. Exact same thing. If you wanted to solve for a leg, though, what you would have to do is you would have to subtract one of your legs from both sides, and then you would square root both sides. So here we can see that we got the hypotenuse squared minus a leg squared. So again, make sure that you square or use your exponents first before you subtract. Really doesn't matter which leg is which, so actually these last two formulas are basically the same. I mean, the only difference is the letters, but the pieces being used are no different in each of those last two equations. You really only have these two different forms here. If you want to solve for the hypotenuse, square your legs and add them together and then square root. If you want to solve for a leg, make sure that you subtract the leg squared from the hypotenuse squared. Again, making sure that you square your hypotenuse and your leg first before you subtract. So the big difference there is the addition and the subtraction. If you don't like that, if that's confusing and too much for you, well then just start with a squared plus b squared equals c squared. And I could show you two different ways that we could use that. All right, let's do some examples here. In this first example, let's make sure that we label our pieces, figure out what we are solving for and what we have to use. Always find that right angle, look across from it, and label that side the hypotenuse, or C. Then label your other two sides the legs, or A and B. Doesn't matter which is which. So we're missing a leg. We're going to solve for that. So the simplest way to go about it is just start with our standard form, a squared plus b squared equals c squared. So I'm going to take x squared and 3 squared. I'm going to set them up so they're being added on one side, putting my legs on one side. And then on the other side, I'm putting the hypotenuse squared all by itself. So you could simplify. You could say 3 squared is 9, 5 squared is 25, And you could subtract 9 from 25 there, and you would get 16. And then you could square root both sides. And the square root of 16 is 4. I want to, however, push an algebraic approach. So what I'm going to do is I'm going to move things algebraically first, and then I'm going to simplify. So I'm going to take this 3 squared that's being added, and I'm going to move it by subtracting from both sides. So now I have 5 squared minus 3 squared. To get x alone or by itself, I need to undo my square here. So I'm going to square root both sides. And now I know that my side length here is going to be whatever the square root of 5 squared minus 3 squared is. So I need to use my exponents first before I subtract. Make sure you don't say that 5 squared minus 3 squared is 2 squared. That's not true. 5 squared is 25. 3 squared is 9. Now I subtract, and I get 16. And the square root of 16 to finish it off gives me 4. So now I can see that the lengths of my right triangle here are 3, 4, and 5. That's actually a special right triangle. Its name is the 3, 4, 5 right triangle, describing the ratio of the sides. And this one is typically used quite often on worksheets, on websites, and textbooks. If you can recognize it and you're comfortable enough with it, then you can skip the Pythagorean theorem because you already know what the side length is. For example, if I had a blank 4 or 5, I know I'm missing a side length of 3. Or if I had a 3 blank 5, I know I'd be missing 4. Or 3, 4 blank, I know I'm missing a 5 there. As you get more and more comfortable recognizing those triangles, then you can skip this Pythagorean theorem step because you already know the ratio of the sides. Any factor or any scale factor of that is also true. So if you double the ratio, you would get 6, 8, 10. If you triple it, 9, 12, 15, that's also true. A little bit harder to recognize when you start scaling it, but eventually, if you see it enough, you can recognize it. All right, the next one. Again, let's label the pieces that we know. So cross from the right angles the hypotenuse. Let's label the other 2 sides as our legs. So this time we need to solve for the hypotenuse. So we know that we're just going to add the squares of our legs and square root it to get it. So we'll take 5 squared plus 12 squared. Legs squared being added on one side of the equation. Our hypotenuse squared all by itself on the other side. If I square root both sides, well, then the hypotenuse, again, is going to be the square root of the sum of the squares of the legs. Do your exponents first. 5 squared is 25. 12 squared is 144. Now we can add. We get 169, and the square root of 169 is 13. So we can see that the side lengths of this right triangle are 5, 12, 13, and that is another pretty well-known special right triangle. These two are certainly the most popular, the 3, 4, 5 being the most popular, 5, 12, 13 coming in second. There are others that are always whole number lengths there, but these are certainly used the most. Again, if you can recognize them, maybe it saves you some time in using the Pythagorean theorem. But if you ever forget or don't recognize it, Pythagorean theorem will always prove it to you. All right, after those special ones, things get a little weird. Outside of that, we may get irrational side lengths that are decimal values. We're going to keep them in radical form, continuing to practice simplifying square roots here. If we label the pieces that we know here, cross from the right angles our hypotenuse. 9 and x are going to be our legs. So let's take x squared and 9 squared on one side of the equation, and 16 squared on the other side by itself. Again, practicing the algebra, although you're more than welcome to simplify and then use algebra. If I subtract 9 squared from both sides, then I have 16 squared minus 9 squared. To get x by itself, to undo that square, I'm going to square root both sides. So now I know that my side length there is going to be the square root of the difference of my squares here. So again, solving for a leg means that I'm going to take the hypotenuse squared minus the leg squared. Whereas if I'm solving for the hypotenuse, I take the sum of my legs squared. I'm adding. All right, so 16 squared is 256. 9 squared is 81. The difference of those two numbers is 175. 175, if I square root it, is going to give me an irrational radical or an irrational decimal. So what I want to do is I want to factor it and simplify it and keep it in radical form. I can also use an approximated decimal form, but let's do both. To simplify the square root of 175, I need to be dividing by my perfect squares. So if I can divide by 4, no. Can I divide by 9? No. What about 16? No. I can divide by 25. So 25 is the first perfect square that I can factor this. 25 times 7 is the factor pair there. Give each of those their own square root to help you simplify. The square root of 25 is 5. And 7 stays behind under the square root. I could take that, do 5 times the square root of 7 on my calculator to get its approximate decimal value. Or I could back up here and take the square root of 175. It gives me the same answer. All of these values are the same thing, just represented 3 different ways. Unsimplified, simplified, and decimal form. All right, one more time. This time, one of our legs has a irrational radical value. So we've been practicing squaring a value like this. So let's apply that. Labeling our parts, across from the right angle is our hypotenuse. So these are our 2 legs. Let's take those values and square them and add them together on one side. And set the hypotenuse squared equal on the other. 11 squared is 121. If I square this value here, I'm going to do 5 squared, which is 25, and I'm squaring the square root of 2. If I square a square root, they cancel each other. I'm just left with 2. So this turns into 25 times 2, which is just 50. So now I can add 121 and 50 and get 171. I can then square root both sides. Square root of 171 is an irrational decimal, so let's see if we can factor. Can we divide it by 4? No, but we can divide it by 9. 9 times 19 is the square root of 71. So the square root of 9 can be simplified to just 3. Square root of 19 stays behind. You could then multiply 3 times the square root of 19. Or you could square root 171. Either way, it'll give you your approximate decimal value. All right, so if you can use the Pythagorean Theorem a variety of different ways like we just practiced, well, then you can solve any application involving Pythagorean Theorem. Here's your first example. Let's say that a utility tower of some kind has a support cable. And that support cable is attached 8 feet from the top of the pole. So if I count backwards from the top 8 feet and attach my support cable, I'm going to bring that support cable that is 60 feet long. I'm going to bring it down and anchor it into the ground 48 feet from the base of the pole. So now we can see that we have a right triangle here, and we're going to add 8 feet to this side length of the right triangle to get the height of the pole. So the height is going to be whatever the side length of the triangle is, x, plus another 8 feet. So let's solve for x here, just that part of the right triangle. We know the hypotenuse, and we know one of the legs, and we're going to solve for another leg. So knowing that we're solving for a leg, we can say that's going to be the square root of the hypotenuse squared minus the leg squared. Or if we're not quite comfy with that, we could back up to a squared plus b squared equals c squared. Subtract 48 squared from both sides, and then square root both sides. And now we're back to where we could have started. Square your values first before you subtract. The difference of those squares is 1,296. Square root that, and we get 36. So up to that part on our pole is 36 feet. Let's add that extra 8 feet to get to the top. So our pole is 44 feet high. One more example here. That last example was using a vertical length. This time we can imagine we're taking a bird's eye view of something and finding a horizontal length. Let's pretend that we are leaving school with a friend and we are walking 45 yards north straight up. Our friend is walking 60 yards east or to the right. And the question is, how far apart are we now? So we're going to find that hypotenuse length, but we're also going to convert it to feet. So we're in yards right now, so we'll do a conversion at the end there. I mean, you could convert these to feet first and then solve it. That's certainly possible. I'm going to use yards and then convert second. So needing to solve for the hypotenuse, I know that I'm going to take the square root of the sum of the squares of my two legs, or I can start with a squared plus b squared equals c squared, and then square root both sides, and now I'm at the next step. Exponents before your sum here, so 45 squared and 60 squared. Find the sum, add those two together, we get 5,625. Square root both sides. Just square root that value, we get 75. Remember that we're in yards right now. So let's convert it to feet. There are 3 feet in every yard. So in 2 yards, we must have 6 feet. 3 yards would be 9 feet. So we're getting bigger if we want to go to feet, so we're going to have to multiply. Or if you weren't quite sure if you were multiplying or dividing to convert, you can create a proportion. If there's 3 feet in 1 yard, set that equal to your next ratio, making sure that corresponding things are in the same spot. So yards on top, feet on the bottom. Although you could flip both of these ratios, put feet on top and yards on the bottom, that would be okay. Cross multiply to solve a proportion. So 1 times x is x. 3 times 75 is going to give us our distance, 225 feet. All right. So there's how we can use Pythagorean theorem to solve for some applications. Be sure that you can identify the parts of your right triangle and set up your Pythagorean theorem by putting those parts in the right spot. Keep practicing the Pythagorean theorem and then take a chance at solving some application problems. Interpreting word problems, drawing a picture, creating a right triangle, and solving for the missing piece.